the function from the real numbers to the real numbers is continuous at a point A if the limiting value that the function has as x approaches A is exactly the same as the value of the function at A. Okay, so there's no sudden jump, so there's nothing funny going on with the function that stops its limiting behavior as the argument x approaches some limiting argument. That limiting behavior of the function will be exactly the value that the function has at that point. Okay, so that's the idea of continuous. And so some things that are not continuous. Well, back a few pages, we looked at the graph of a function like this. This is a piecewise linear graph, which is a graph made up of a couple of straight line segments. But you can see that the function makes a sudden jump in value at the argument x equals 1. So if the value a was your 1 there, the limiting value of the function as x approaches a is certainly not equal to the value of the function at 1. The value of the function at 1 there is indicated as 3, the filled in dot there, and there isn't even a unique limiting behavior of the function as x approaches 1, because it depends. If you approach it only from the left-hand side, you're approaching the value 2. If you approach it only from the right-hand side, you're approaching f of x is approaching 4. So it's a bit ambiguous what the limiting behavior of the function is. And anyway, neither of the two possible options are equal to the actual value of the function at that point. Another example of so any function which takes a sudden non-continuous jump in value like that, that's an example of a function which isn't continuous. Okay. Another example was where you've got the function kind of breaks down in a slightly different way. So this graph, well, this was kind of an attempt to draw a graph of the function sine of 1 over x. So we went through this example before Christmas, so I won't go through the whole explanation of it again. But sine, we know, is a periodic function which varies in value between 1 and 1, 1 and minus 1, and it does so continuously. But if you form the argument 1 over x and evaluate sine at 1 over x, then as x approaches 0, you see the number 1 over x is divergent. It's getting larger and larger without any upper bound. So sine of it, as you approach 0, sine is going to have to go through, an infinite number of periods, infinite number of oscillations as you approach 0. So that's what's trying to be plotted there, although it's not a very accurate plot. But you can see it starts going up and down as you approach 0, and it's going up and down ever faster and faster and faster. So now the function is continuous everywhere, but there's a question about what's going on at 0. Well, there is the fact that the function is undefined. As it stands, the function is undefined at 0, okay, because 1 over 0 is not a real number. So sine of 1 over 0 doesn't make any sense. But even if you were to supply a value to the function, even if you were to say that, okay, well, the function is sine of 1 over x everywhere away from 0, but at 0 itself, it's equal to some other value. Even if you were to supply a value, no matter what value you supply, you could never make the function continuous at x equals 0, okay? Because the limiting behavior of the function as it approaches 0, well, there is no limit to the function values because they're just oscillating between 1 and minus 1 at an ever-increasing rate as you approach 0. So there is no limit, okay? So the limiting value of the function doesn't exist. So that function is certainly could never be made. There's no way of fixing this to make it continuous if we wanted to have the value sine of 1 over x everywhere away from 0. Okay. Now this is all leading us towards the idea of differentiation and the derivative of a function. And then we'll also look, so we looked at this last time, we looked at two properties of continuity. And so these are kind of reminiscent of the properties of convergence that we've looked at before in sequences and series and so on. and then a new one in theorem 4.4 to do a composition. So theorem 4.3 says that continuity, well, the operations that you can do with functions, which are sums, products, and quotients. So you can take a pair of functions, you can add them together. You can take a pair of functions, you can multiply them together. You can take a pair of functions, you can divide one by the other as long as the one you're putting in the denominator stays away from 0. Well, those operations preserve continuity. Okay, so if the two functions that you start off with are continuous at a point, then any of these new functions, the sum function, f plus g, the product function, f times g, quotient function, f over g, those functions themselves will be continuous at the point as well. Theorem 4.4 concerns the very important operation amongst functions of composition. Okay, so when you compose two functions, you run one function after the other. So you apply, so what are we talking about there? There we're talking about the composition g after f in theorem 4.4. Okay, so g after f is a new function. G after f evaluated at an argument x is simply g of f of x, g of f of x. And that theorem says that, well, if g and f are both continuous at the appropriate places, that if f is continuous at x and g is continuous at, sorry, if f was continuous at a and g is continuous at f of a, then when you run the two functions together, the composition function will be continuous at x equals a. So those theorems tell us that continuity kind of fits well with the operations we can do amongst functions. Okay, so the operations that combine functions to produce new functions, sums, products, quotients, composition, and all of these operations fit well with the concept of continuity. Now, to prove these, we have to engage with the formal definition of continuity. Okay, so this is where we kind of ended last time by looking at this. So the last lecture we gave was looking at this formal definition of continuity and explaining it. So you'll recall it's a bit of a kind of a logical mouthful, the formal definition of continuity, but we explained it with the aid of some diagrams. And I'll just show those again to you now. So the formal definition of continuity, so this is saying that the function f is continuous at a point x equals a in its domain. And the logical definition is given there in that predicate calculus statement, predicate logical statement there. It says for every epsilon greater than 0, there exists a delta greater than 0, such that x minus a less than delta implies that absolute value of f of x minus f of a is less than epsilon. Okay. Now, what does all that mean? Well, what that's saying, one way to interpret it is to think about it as describing some of the geometrical properties of the graph of the function. Okay. These are some of the things we looked at last time. I'll just show you, just remind you of what we talked about. So these are the lecture pages I produced. Okay, so it's this kind of picture. Oops, okay. This kind of picture here. So we want to look at that formal definition of continuity and comparing it to this kind of picture here. What it's saying is that, so here we have x equals a, the point in the domain of f. We've got the graph of f, we can see there, a nice continuous looking graph. And somewhere in the codomain, the vertical axis, we've got the value f of a. And what the formal definition of continuity is saying is that for any value of epsilon, now epsilon we think of as a radius distance around the point f of a. So epsilon is the radius of an interval which we're going to position around the point f of a. Okay. And epsilon can be any positive number, so it can be very, very small. We can be talking about a very tight interval around f of a. I've just drawn a fairly largish one there so you can see it clearly on the diagram. And what it says is that, what the definition says is that no matter what value of epsilon you choose, no matter what strictly positive value of epsilon you choose, there will always exist a delta. Now the delta is the radius of an interval around the point x equals a in the domain of the function. It says there will always exist a delta with a certain property. And the property is that the function maps the whole of this interval. So we're talking about this segment of the graph of the function. It maps the whole of that interval. If you look at where the image of that interval is, see the image of its leftmost point, a minus delta, is down here. The image of a plus delta is up here. But whatever range of values in the codomain is covered when you apply the function f to this interval, the property that this delta has is that when you apply the function f to it, everything which started off inside this interval ends up inside the epsilon interval over here. Okay? And no matter how small that epsilon is, even if we shrunk it right down to extremely close to the point either side of f of a, if we dealt with a very small epsilon, okay, we'd have to make delta very small, but there would exist a delta. This is what the definition is saying. It says there would exist a delta such that when you applied f to any argument inside the delta interval, it would go to inside the epsilon interval. Okay. So if that property, if that is true of the function, then we say it's continuous at x equals a. That's the formal definition. Okay. So it introduces these two parameters, delta and epsilon, which indicate or describe the way that the argument of the function is getting closer and closer to a, and the value of the function is f of x is getting closer and closer to f of a. Okay, so it names those two parameters and allows you to talk about it. Now it's important to remember the logical order of the two. So the statement is for every value of epsilon, there will exist some delta. Okay? So different values of epsilon may lead to different values of delta. And in general, the kind of feeling is that the smaller epsilon gets, the smaller you'll be required to make delta. Okay. We also drew a diagram there. Let's look at this again, which showed us how a non-continuous function, so a function with this kind of sudden jump in value, how that violates that formal definition as well. Whenever you see a new definition, it's important to see it from both sides, from the kind of positive side, looking at things that satisfy the definition, but also from the negative side, looking at places where the definition is broken or situations that don't satisfy the definition. So this is a graph of a function here. You can see the function is wobbling along left of x equals a, and then suddenly at x equals a, it makes a sudden jump up to a higher value and then wobbles along continuously to the right of that. Okay, so there's a problem at x equals a. There's a jump, sudden, discontinuous, immediate jump in value of the function. Now by the filled in circles there, I've indicated that the value of the function f at x equals a is actually the higher value. So you can see that drawn there in the codomain, f of a. So how is this breaking out? So the point to appreciate from this is how it is that this situation is violating that formal definition of continuity. Well, we can see that because no matter how small we make epsilon, so there in red I've drawn the upper and lower limits of an interval around f of a. So we've got f of a plus epsilon, f of a minus epsilon. No matter how small that epsilon gets, inside any delta interval, so here, I haven't written the deltas on it, but here we've got an interval around x equals a. Now, no matter how small you shrink that interval, there will always be points in it that are to the left of a, that are slightly less than a. Okay? But when you apply f to those points, you're going to get something which is close to this lower value. So you're definitely going to get something which is outside of the red interval there. Okay? No matter how, even if I shrink my delta really, really tiny, but because it has to be strictly bigger than 0, there'll always be something slightly to the left of a. And that will always produce an f value, which is down around here, so which is certainly outside of the epsilon interval. So it's not true that for every epsilon, you can find a delta such that f of the delta interval goes inside the epsilon interval. There are some epsilon for which you could do that. If you chose epsilon really, really big, so that the epsilon interval came down below this value here, where the function is for arguments less than a. You chose epsilon so that it crept down to below that. Then for those values of epsilon, there would exist a delta satisfying the theorem, satisfying the definition. But the definition says for every value of epsilon, it must be possible to find a delta. Okay, so as is shown there, for this kind of situation, there will be some values of epsilon. Once epsilon gets kind of small, and once it leaves behind this value down here, where the function is at to the left of a, then no value of delta that you're going to choose is going to do the job. Okay, f of this interval here, f of anything to the left of x equals a will always be outside the epsilon interval. You can make the things to the right of x equals a, they can go inside the interval, fine enough, but it must be so for every value of x in this interval. So that's illustrating how discontinuous functions fail or violate that formal definition of continuity. Okay. So we're introducing that formal definition of continuity just so we can see the real deal, so to speak, see the actual technical definition, but also so that we can rigorously prove a couple of these properties of continuity. That's what I'd like to go to now, to show you how that formal definition is kind of put together, how you use it to prove these preservation of continuity type results. Okay, so we'll look at the theorem 4.3 first. I might improve all the cases. I might just show you one or two as examples. I think I'll do the sums and products one, maybe. So I'll get this screen up. Remember how to do that? It's not working. There was some funny thing last term that this stopped working, wasn't it? Yeah. Oh no, sorry, no, I'm just doing it now. Document can. Sorry, forgotten how to use this after the break. Okay, so we're looking at theorem 4.3. And we're going to do the sums version or the linear combinations version, okay? So this is the proof for linear combinations. So let's just be clear on what we're starting off with. We're starting off with f and g are two functions from the real numbers to the real numbers that are both continuous. Are both continuous at the argument x equals a. We're going to give ourselves two scalar numbers, just two fixed coefficients, if you like, an alpha and a beta. And we will prove that alpha f plus beta g, so this new function, this new linear combination of the old functions f and g, is also continuous. Is also continuous at x equals a. Now it's going to involve applying that definition. So we know that the formal definition is satisfied by f and g on their own. And we now want to prove that the formal definition, I'll get it up on the screen. this formal definition there is satisfied for this new function. So we want to show, what we want to try and demonstrate is that this statement is true. Instead of the function f there, we want to have the function alpha f plus beta g. So rather than just diving straight into it, because this definition, it all centers around this final inequality here, this f of x minus f of a less than epsilon. So just before we launch into it, which will kind of motivate the proof and explain why we make the choices we do, we'll just examine this, examine the absolute value inequality that we're going to be trying to establish, okay? So first we examine the appropriate P's aren't too clear. First, we examine the appropriate absolute value inequality. So what am I talking about there? I'm talking about this inequality, which is alpha f plus beta g, this new function evaluated at x, minus its value evaluated at a, this absolute value. Now, when we come to prove that alpha f plus beta g is continuous, we'll want to be proving under certain conditions, under a choice of an epsilon, show there exists a delta such that blah, blah, blah. But ultimately, we're going to want to be able to control the size of this inequality. So we're going to, the size of that absolute value. So we're going to have to prove that that absolute value is strictly less than epsilon. So how do we control the size of this this absolute value? Well, we make use of the fact that we know that f and g are continuous. So we know, I know that I can control the size of f of x minus f of a, its absolute value. And I also know that I can control the size of g of x minus g of a. So the idea is to see, is to appreciate how this absolute value, differences here, can be written as an appropriate combination of the absolute value of the differences of the f function values and the g function values. So the first thing to do is to, expand these brackets a bit. Okay, so expand the definition of the sum of two functions, adding two functions together. So we can do that. So alpha f plus beta g evaluated at x is simply alpha times f of x plus beta times g of x. And this is minus alpha times f of a minus beta times g of a. Now there's lots of things in brackets here, but you need to be clear, f and g are functions. So f bracket x, g bracket x, that's a function evaluated at an argument. The alpha and beta are just real numbers. So this is just what's going on here with alpha bracket f of x. That's just indicating the number alpha multiplied by the number f of x. When you're reading these things, you have to be alive to what the different objects are. F and g are functions. Alpha and beta are just fixed real numbers. Yeah. So this is beta multiplied by the number g of x. And so as I've said, I know how to control the values of f of x, the absolute value of f of x minus a, and the absolute value of g of x minus g of a. We can see them floating around there. But just to see it clearly, we want to bring them together. So we want to bring all the f's together and bring all the g's together. So we just kind of reorganize this like so. So it's plus beta. So that's just shifting things around so the f's are all together and the g's are all together. now this is an absolute value, and I want to control the size of the absolute value. So I can make use of a very important property of absolute value of sums or absolute value of differences, and that's the triangle inequality. And that says that the absolute value of a sum is less than the sum of the absolute values. Okay? So I can say this is strictly less than, well, I can do a few things here. I can take the absolute value of A out, say absolute value of f of x minus f of A, plus absolute value of B, and then absolute value of g of x minus g of A. So that's using the triangle inequality. So the triangle inequality says absolute value of z1 plus z2 is, sorry, less than or equal to the absolute value of z1 plus the absolute value of z2. Less than or equal to, sorry. So using the triangle inequality and the product property, namely that the absolute value of z1 multiplied by z2 is equal to the absolute value of z1 multiplied by the absolute value of z2. These are all true for every pair of real numbers. So true in lots of other, for absolute value like operations, these properties also hold in many other contexts, not just with real numbers, but with lots of other type objects as well. But we're just talking about real quantities here. So, yeah, this is the point. I said that when I want to prove that alpha f plus beta g is continuous, I'm going to have to control the size of this absolute value. So ultimately, I'm going to have to force it to be less than some prescribed quantity epsilon. Well, here I've shown that it's no bigger than this quantity here. But this quantity here is a linear combination of absolute value of f of x minus f of a, absolute value of g of x minus g of a. But the point is, I know f is continuous at a, I know g is continuous at a. So I'm able to control the size of these two quantities here. So if I can make these two quantities as small as I want, and these are providing an upper bound for this quantity up here, then I should be able to make this quantity as small as I want. Okay? So that's the key point. I'll just underline that absolute value, underline this one, and just make a little note here. Notice we can control the size of these two absolute values. Okay, now yeah, I'll just refer back to this sequence of equations here later on. I won't want to write all those out again. So now we can start to approach the proof that alpha f plus beta g is continuous. So we'll start. We'll say let epsilon greater than 0 be given. So somebody gives you an epsilon. We have to find the delta, which makes the whole thing work. We want to find the delta such that if x minus a is less than delta, then this inequality is smaller than this absolute value is smaller than epsilon. And I'm going to do that by controlling the size of these two. So I can say since f and g are continuous at x equals a, we know that there exists delta 1 and delta 2 with the following properties. So such that, and what property do delta 1 and delta 2? Which delta 1 and delta 2 am I going to choose? Well, the delta 1 is going to be one that influences the size of absolute value of f of x minus f of a. And I'm going to choose the delta 1 that makes this smaller than epsilon over 2 times the absolute value of alpha. Remember, f is continuous at a. So for any epsilon, I can choose a delta which will make f of x minus f of a smaller than that epsilon. So here, I'm not using the epsilon, which is stated up here. I'm using a variant on it, epsilon over 2 times the absolute value of alpha. That's just still a positive number. And this inequality, because f is continuous, this statement holds for every epsilon. So here, I'm calling on it for this value of epsilon. And the property that delta 2 has is that if x minus a is less than delta 2, that implies that g of x minus g of a is less than epsilon over 2 times the absolute value of beta. They're wondering, well, why have you chosen epsilon over 2 times the absolute value of alpha? Why have you chosen epsilon over 2 times the absolute value of beta? Well, if you look back up a couple of lines, you'll start to appreciate the reason for that choice. Now I know that as long as I'm close enough to A, so that these two inequalities are satisfied, I'll be able to replace this. This absolute value here is not going to get any bigger than epsilon over 2 times alpha. This absolute value over here is not going to get any bigger than epsilon over 2 times beta. So this whole quantity here, you multiply the first one by alpha, the second one by beta, this whole quantity here won't get any bigger than epsilon over 2 plus epsilon over 2. So therefore, the whole thing won't be any bigger than epsilon. But this whole thing is at least as big as this thing here. So if this thing is not bigger than epsilon, then this won't be bigger than epsilon. And that's the one I need for the formal definition of continuity applied to alpha f plus beta g. But now I have to be sure that I can call on these two facts at the same time. They're both governed by these two quantities, delta 1 and delta 2. So now we choose, or now we let, it's almost like a programming language, writing a program in MATLAB or something, we let delta be equal to the minimum of these two quantities, delta 1 and delta 2. Delta 1 and delta 2 are just two real numbers. I don't know what they are, but I can set my delta, this is going to be the delta which appears in the final definition of continuity. I set it to be the smaller of these two. So if x minus a is less than delta, well, if it's less than delta, that means it's less than delta 1 and less than delta 2. Okay, because delta is the smaller of them. So that means if x minus a is less than delta, then both of these inequalities here are satisfied. Yeah. So I'm going to start labeling stuff so I don't have to refer back to it all the time. I'll label this as just label those both as 1 asterisk. So if x minus a is less than delta, then both inequalities, both the inequalities at star hold. And so if x minus a is less than delta, then the absolute value, so this is what I want, alpha f plus beta g of x minus alpha f plus beta g of a. This thing, which is less than or equal to, yeah, might as well write it out again, which is less than or equal to absolute value of alpha times absolute value of f of x minus f of a, plus the absolute value of beta times the absolute value of g of x minus g of a. Well, this now becomes strictly less than alpha, and now I have epsilon over 2 times the absolute value of alpha, plus absolute value of beta times epsilon over 2 times the absolute value of beta. And that's true because x minus a is less than delta. Because x minus a is less than delta, both of these inequalities here are true, so I can apply them. And so here, when you add all that together, that's just epsilon. So it's epsilon over 2 plus epsilon over 2. So the claim is that this shows that alpha f plus beta g is continuous at x equals a. Does it really? Well, so in order for it to be continuous at x equals a, this logical statement has to be true. Have I proved this logical statement here? I have to prove for every epsilon there exists a delta such that x minus a less than delta implies absolute value of the function difference is less than epsilon. Have I proved that for alpha f plus beta g? Well, yeah, just look up at what I've written down. I've said let epsilon greater than 0 be given. So I've placed no condition on epsilon apart from the fact that it's positive. So there's no restriction on epsilon apart from that. So everything that follows should apply for every value of epsilon, for every positive value of epsilon. The thing says there exists a delta. Well, how have I shown that there exists a delta? Well, here, I've shown, I said, look, my delta was the minimum of these two deltas. And these two deltas existed because f and g were continuous. So f and g are continuous. So a delta 1 and delta 2 exists with these property. Here's the delta, which kind of magically packages up both their properties. And so now, if x minus a is less than delta, then it was a bit of working out, but ultimately it's that this absolute value of function value differences is strictly less than epsilon. So I know there's less than or equal to here and there's an equals here, but those are just joining each line to the previous line. Ultimately, or overall, the inequality we've shown here is that this quantity here is strictly less than epsilon. So we have demonstrated the formal definition of the continuity that we were required to. Okay, so that's, we can say a QED on that. So before next time, so I'll see you again tomorrow afternoon, won't I? Think about the case of products. So doing this same thing for products of two functions, f times g. So we'll pick that up on Thursday afternoon. You all know about the session at 1 p.m. today, don't you? Yes? Yeah? Good, good. So I'd encourage you all to come along to that. It's kind of like a welcome back session for the new term. I think Norman's got some bit of a kind of recreational quiz arranged. Be a bit of fun. And I think there'll be some important orientation information as well about getting you ready for the second term as well. So it's 1 p.m. What's the room that it's in? E32, was it? E32? Yeah, at 1 p.m. Good. Okay, so I hope to see you all there.